Hello everyone. I'm Elisa Carafiti from the University of Southampton, and it is my pleasure today to have Musard Balliu from KTH. His talk is going to be on how to ensure the security of cloud-based IoT apps. This seminar is a joint seminar with FMSec. FMSec is a formal method network for security. So it is a new network that we are re-establishing together with Joanna, and the plan is to have a joint seminar with UKSPS every month. So every month we plan to have one speaker from the formal methods for security area. And this talk will be in joint collaboration with UKSPS. In the meantime, a bit of advertisement. So we have a website that you can check also on the UKSPS website. We have a Twitter account, and if you go on the website, there is also a way to connect with us. So if you want to be part of the mailing list, please add yourself. We want to have more and more people that are interested in formal methods for security that would like to join the network or would like to have a chat, discussions, or even have a talk. So as I said, it's my great pleasure to have Sai here for this talk. So Sai, the floor is all yours.
Okay, so thank you very much for the invitation. Great pleasure to be here also sort of, in the first ever seminar of the FMSec, so very happy to be here. Today I'm going to talk a little bit about these cloud-based IoT apps and what are the security issues around them. So this is very much joint work with Andrei Sabelfeld's group at Chalmers, Daniel Erdin at Malidaren, and Tamara Resk at INRIA. I shamelessly, now I realize, removed the names of PhD students who did most of the work here, but I'd like to mention Yulia Bastis and also Mohammed Ahmad Panah from Chalmers. But before that, so just to tell you a little bit about my group and what we work on. So the main area is language-based security. So in a nutshell, what we do is trying to apply PL techniques to solve computer security problems. And since we like to sort of have some reasoning ground for what we do is sort of secure in some meaningful sense, then we use a lot of techniques for formal methods. So in a sense, so we want to, when we can, we'd like to get really formal guarantees about these techniques. Otherwise, for large systems, we know that it gets more tricky, right, to make this method scale. So there we look more into bug finding techniques, basically in various areas. So there are a bunch of those that I am mentioning here. So these are things I'll know how to talk about. So if any of you is interested, please reach me out either via email or after the talk. But the focus today is IoT app security. So one framework that we really like and we use a lot in my group is information flow control. So roughly the idea here is that you're given some code basically that handles some sensitive data and produces some public data that maybe people we don't want to, they can access them. And the goal here is to really sort of develop program analysis techniques to prevent basically that these secrets flows to sort of channels that they're not intended to. Roughly, we use techniques ranging from static analysis, so type system, symbolic execution, whatnot, to more dynamic analysis like runtime monitors and so on. So that's sort of roughly what the main focus in my group. But let's get back to the topic of today. So here we're focused on IoT. So I guess this is a super popular buzzword right these days. So I assume you all know about at least what it is. So basically we have this bunch of devices, right, connected to the internet, which is really great. But then when it comes to sort of using them in various aspects, there have been some critique there. In terms of incompatible standards, platforms, and so on. And then if you look broader at the industry level, you know, this kind of fragmentation basically is sort of holding back the market potential for these technologies. But people have thought about this a lot. And one of the limitations they have sort of realized here is that, yeah, connectivity is great, but users are sort of lacking control over what we call digital lives here. So an example would be, and this is sort of a classical example, would be that you have a heart pacemaker of a patient which is connected to a network. On the other hand, you have a doctor also sort of having access to a network, but, you know, if you just take these apps as they are, then sort of, yeah, there is no way to sort of connect the heart pacemaker to the doctor, for instance, sort of notifying in case of the emergency. So this is maybe an extreme example, but it's just to make the point that this kind of connectivity can be really useful here. So as I mentioned, people have thought about this, so how to counter this fragmentation of IoT. And then one of the sort of upcoming standards is what is called the Web of Things. So the idea here is really to connect, have these devices communicate with each other by providing some sort of application support to have them communicate roughly, right? And sort of the great idea here is to have all these devices connected to the web and then look at sort of what we already know about web application protocols to have them interact with each other. Now, for those of you who have sort of done some work on web security or simply read the news, right, you may be aware that this is not sort of particularly famous, right, when it comes to security. So one question we're asking here, so what are the security implications by having these devices connected to the web? Okay. So this is where this idea of IoT apps comes in. So these are sort of very simple reactive applications that have IoT devices and services communicate with each other. So sort of enabling this idea of connecting otherwise unconnected. So to do this, people have investigated IoT platforms, sort of connecting different IoT devices to online services, to social networks, and so on. And maybe one feature of this is that sort of what we want here is really end user programming. So even users maybe with not much experience in programming, they should be able to sort of create and run these apps. There are 4 platforms here that I mentioned. Maybe IFT or If This Then That is the most well-known, but there are others. So probably some of you have heard of. So IFT, as I mentioned, is the most popular. So it's a trigger action platform to have the devices communicating. It integrates over 500 services. So these are all numbers now. More, and it's sort of really running a lot of apps on behalf of millions of users on a daily basis. So let's take a look at how it looks right? So it's really what it says. So if this and that. So if a trigger is sort of triggered, then some action is being performed. So the example I show here is sort of an app that automatically backs up iOS photos to Google Drive. So very useful. You don't want to sort of lose your photos, so you could enable this app and that magic will happen. So, and the question we're asking here is what can go wrong? So the way these two sort of services communicate is by sending information over some cloud platform and then executing some JavaScript code basically to enable this interaction. So obvious question we could ask here is what could go wrong? And so if you have worked a bit with JavaScript, probably you can guess. So the attacker model we are sort of assuming here is a malicious app maker. So it's someone that sort of implement this app in the sort of most malicious way possible, trying to leak out information between different services here. So in this case, we have iOS photos and Google Drive. So somehow the goal of the attacker is to write an app to exfiltrate photos of the user. So how can we do that, right? Here is another example. So very useful app if you have a BMW here. So and you forget where you parked it. So what this app is doing. So yeah, once you park your BMW, then you get an email with a map to the location, basically. And we're asking the same question as before. So yeah, so in this case, I guess user location or the location of the car would be the target of the attacker. Okay. So now this is not that easy, right? Because if you think about JavaScript, then you say, okay, we can simply use one of the APIs to exfiltrate, say, the location to a third-party server. But the developers of this platform have already thought about these security issues. So they use some form of access control here. So on the right, you can see how the app would look like to the user. So the way this works is that the users need to explicitly grant access to the app. So in the example I showed before, you trust this app platform basically to act on your behalf when it comes to accessing your photos and sort of writing to your Google Drive, right, to implement this functionality. So that's good. And one could think that, well, we can still exfiltrate through JavaScript, but the promise here is that JavaScript is sandbox, so you're not allowed to perform any IO operations, among other things. So then the question becomes, well, how can we exfiltrate information in this app? Well, in order to have the apps communicate, so what these app platforms do is they use URLs as sort of a universal glue, basically, to connect things to each other. So let me just show you briefly how this works. So first, when you take a picture with your phone, of course, you've given access to the cloud provider, to the IoT platform provider to act on your behalf. So what will happen is that they will poll sort of the service from your phone, and then it will upload the new image, so the picture you just took, to the IFTTT servers, to the cloud platform, basically. So once that's done, then it will put up the image under a URL, which is public, but it contains a long random string, basically. So it's sort of, you can safely assume it's unguessable here. And then once that's done, then it will just pass this sort of public but unguessable URL to the Google Drive API, which will sort of retrieve the photo and just say, sort of store it into the system. So yeah, so since the code is sandboxed here, then it becomes a bit tricky, right? So how do you exfiltrate secrets in this setting, right? So there are a lot of sensitive sources here. So you could think of location, voice commands, images, video feeds, and so on. But you cannot directly sort of exfiltrate them because this JavaScript is supposed to be sandboxed here. So one could think, okay, we could use public sync. So if you manage to trick the user to install an app that maybe, you know, post the photo on a public Google Drive, right, and other users can access it, but yeah, so that's not very stealthy in a sense. So in a sense, right, we're in a setting when we can sort of load the gun, but cannot pull the trigger here because we can write whatever JavaScript code we like, but sort of, yeah, it's sandbox, so we cannot exfiltrate information. So what do? Well, the idea of the attack here is pretty simple. We really use the mechanism that sort of the platform uses to have services communicating as a feature for implementing the attack. So what's going to happen here is that, so remember the app is, if the user takes a picture, then store it on Google Drive. So one type of attack is what we call the URL upload attack. So when the photo is uploaded to the servers of the platform in this case, then what one could do is simply sort of specify an attacker-controlled server passing as a parameter the URL of the photo. Okay, so what could happen in this case is that, well, this would simply send a request first to the attacker-controlled server, which will store the photo and then just pass it over to Google Drive to sort of store the image as expected. So sort of completely stealthy to the user of this app. Another attack vector here, which is maybe a little bit less stealthy, but not much when it comes to sort of everyday users, is the URL markup attack. So here the idea is the same. You pass the secret as a parameter to request to an attacker control server, through an image which is 0 times 0 pixel. So what happens is that when this sort of app gets when the result sort of gets rendered on the email client, say of a user, then this will be sort of completely invisible, but on the image will be totally invisible. But on the other hand, the secret will be sort of sent to the attacker. Now, if you monitor network requests and so on, you could capture this, but otherwise it's completely unnoticeable to the user. So to convince you about this, I'll take the risk and sort of play a live demo with you just to show you a little bit how this platform works. So let's hope it will work. So here is how this system works. So you have a web interface, but you could use a smartphone client as well. And you can create these apps, or they're called Applet in this system, as you like. And one of those, which I have already created, is called Android to Dropbox. So since I don't have an iOS phone, so the functionality I would like to have here is that each time I take a photo with my Android phone, then it should store it in Dropbox. Okay. So let's see how this looks like first. So you have this trigger. So if I take any new photo, then it should add a file from URL to my Dropbox in this case. So if we take a closer look at this then part, then what's happening here is that instead of just passing the URL directly as expected, I'll pass it to my attacker control server here, which will sort of store the photo locally, and then it will pass it to my Google Drive. Okay. So that's the idea. So here is my attacker control server. So there is nothing in it. And here is my Dropbox, which contains only one picture, which I sort of used later to check that everything was working. Okay. So now what I do as a user, well, I install this app. So let me just go back here. And then I connect it, okay? So what this means is that now it's active on my smartphone client in this case. And then what I'm going to do now is sort of to take a picture of the wonderful view from my office. And then let's see what's, if this is going to work, basically. So now the app, I took a picture, so now the app should have executed. And I should be able to hopefully see that the picture was stored on my Dropbox. Let's see if this is coming. Okay, so let's look at Dropbox. So here is the picture I just took. So as a user, right, so this is completely stealthy. So it did its job in a sense, but then when you look at the attacker control server, so you get access to this public URL. Okay, so pretty simple, and you could sort of have a similar attack basically when it comes to images, so to using markup as I showed before. Okay, yeah, so I'll skip the demo here for sort of time reasons, but you can do this on different platforms. So if we just consider a simple attack, right, and just look at the attack surface, well, that's quite tricky because these systems, they handle a lot of private information ranging from locations to emails to, you know, social network feeds, voice assistants, surveillance cameras, and so on. So it's tricky. My focus here was mainly on privacy, but you could think of similar attacks when it comes to integrity and availability. For instance, you know, changing the file that's going to be stored on Google Drive and so on and so forth. This is less stealthy, but you know, it can, basically have consequences. Okay, so what we did here is let's see a bit how prevalent, you know, this kind of attacks could be in IFT platforms. So we sort of crawled around 280,000 apps developed by different users. The vast majority here, 98%, are developed by third-party users, so could be malicious. And then we look at all these triggers basically. So classify them, what could be private, integrity sensitive, availability sensitive. And after this classification, well, we run the analysis to find that 30% of these apps are potentially vulnerable when it comes to privacy, which is quite bad. Another type of attack, which was a bit surprising here, was URL shortening. So I guess, I assume you have all heard about these shortened URLs, right? It's a technique to shorten long URLs for different reasons on the web, and then use redirects basically to direct the user to the original page. So since the URL that is being created, say when uploading the photo, is sort of public, and then it used to be permanent at the time, well, if you shorten those, and the way IFTTT is doing this is by assigning a seven character ASCII string, basically, where the first character is always a 7, okay? So what this means is that you have an entropy of 6 characters. So sort of something we tried out here is to just randomly basically check for characters of length, for strings of length 6. And then it turned out that upon 1,000 requests here, we have around 2.5% success rate. So this really allows for large-scale scraping of private information. And then at the time, this system was not very well designed, so these URLs were really being served over HTTP. So network attacker could do much more damage there. Okay, so once we identify the problem, then we want to study some countermeasures, right? So really in the beginning, if you want to help them, of course, you can not push for your fancy sort of formal methods technique, but something that is usable and sort of fixes the problem immediately. So one sort of classification here that could be useful is sort of by looking at the sensitivity of the sources, you can say that, well, if an app does not access any private sources, then, then it's fine. So it can just keep executing. Otherwise, you can disable basically this JavaScript code that is being used to customize this interaction. And for URLs, you just want to increase the entropy. So an example here. So if the app is sort of sending a notification each time an astronaut enters space, well, it's not very sensitive. So in this case, it's just fine. Otherwise, if it's tampering with the location, so maybe one wants to disable JavaScript. Okay. But in long term, of course, we like program analysis and formal methods. So we're sort of thinking that techniques based on information flow control could help here. And this is really about tracking how information is being propagated in JavaScript and making sure that, if the photo URL at some point gets passed to the sink, then just stop the execution, basically. So to do this, we extended an existing information flow tracker called JSFlow, developed at Chalmers, and sort of experimented with that when it comes to apps from IFTTT in this case. So maybe something to point out here is that so the code is not very large. So we're talking about, in worst case, maybe 100 lines of code. So that's sort of the dream for people working in formal methods, I guess. So in this case, really, these apps are within the reach, of techniques that we know today. So this is part of sort of types of ways how you can exfiltrate information. So this is just for completeness here. So I think I'll just go pretty quickly and just mention basically what are the possible ways. So you could encode information in the control flow structure of the program. You could leak through the presence, of an event in the program. For instance, if the attacker wants to learn whether, your kids are at home, he just, needs to implement an app that sort of, either executes or not, depending on such event, for instance. Timeouts are another sort of possible attack vector here. But what is more interesting is timing. So Imagine if you had all these sort of fancy controls that prevent both implicit flows and explicit flows, so you cannot leak out information in a direct way. Well, it turns out that you could leak through timing. So by measuring the execution time of the program, basically, it's what we found out here is that you could leak, you could exfiltrate strings up to 350 bits, which if you translate to ASCII is 50 characters here. So I'm not going through the code here, but it's pretty straightforward. So you have some secret, and then what you do is, depending on each bit in that secret, you either run a long or a short computation, and then you just measure the time. What is interesting in this setting is that since these apps are being executed in the cloud, so the attacker has no way of knowing when the computation started. So this gives some flexibility, basically, when it comes to allowing patterns that are usually used in implementing this app. So I do have a reference here of a paper from CSF 2 years ago, where we sort of study these patterns, getting also strong guarantees when it comes to timing attacks. So what's the vision here? Well, when it comes to formal techniques, really what we'd like to do is to have a platform based on maybe static or dynamic analysis that tells the user, you know, if something wrong, analyzes the code, and then in our case by information flow control, and if something wrong happens, then sort of it notifies either the user or, you know, the owners of this platform. So of course, since we like Greek letters and formal methods, so what we've done here is developed information flow monitor in practice, but also formalized security guarantees when it comes to soundness and permissiveness of the monitor. So just to emphasize again here, since these are low-code applications, as they call them today, you know, at least for the apps we tried, is that there were no false negatives, but that's sort of expected by our monitor. But also when it came to false positives, the number was very low. So we had a single one, and this was based on an artificial example that we wanted to sort of play with. We notified IFT and other platforms about this, so they responded very quickly and managed to fix the bug here. Not deploying our techniques on tracking the information, but they took other countermeasures, improving the access control. So just to summarize this part, so this new area of cloud-based IoT platforms opens up for new opportunities, but unfortunately, there are obvious attacks there. So I mentioned URL upload attacks, URL markup attacks, and this URL shortening. So we find in this empirical study that 30% could be sort of subject to privacy violations, really unnoticeable to the users, and studied some countermeasures for long and short term, basically. So if you're interested to learn a bit more about this, then there is a sort of popular science kind of paper from IEEE Security and Privacy magazine, and the attacks we described in this CCS paper from 2018. Okay, so I think if you have any questions, I think this is a good point to ask them. Otherwise, I'll try to go a bit further with some attacks here. Any questions?
Hi, I just had a very quick question. Thank you. That was a fantastic talk. So we also used if this and that. So why not use encrypted channels between applications? So for example, if I just encrypted the data between apps, could some of these issues that you address be overcome using that approach? Thank you.
So with encryption here, I guess you mean having some sort of authorization, right? When the data is passed to a service, right?
Yeah, it could be a TLS channel or a
yes.
TLS, or it could also be like a key exchange that occurs that allows you to encrypt the content so that any intermediary could not see So if you redirected it as you did in your scenario, you wouldn't be able to see the content.
So I think the issue here is that for you need to access this data, right, in the cloud platform. So there is this JavaScript code that has to do something with the data. So in the example I showed you, you're correct. So if one encrypts the photo, right, then yeah, there is not much to do there. But for example, with location, so one of the classical scenarios is that you use location, for instance, to check, you know, whether some sort of geofence, right, yeah, the user is in some sort of geofence. So in this case, the application has to have access to the location. So then it would become a bit tricky, at least from usability perspective, right, to not to reveal the data. Does that make sense? Or?
Sure. No, that sounds good. Okay. Thank you very much. Thank you.
Okay.
Yeah.
Any
So
other?
yeah, just a continuation of what Omar asked. So if you encrypt the data, implicit or timing leaks are still possible, isn't it?
If I encrypt the data again?
Yeah, even if you encrypt the data, even if you send the data on the encrypted channel, the attacker could still learn via timing and other implicit covert channels.
Yeah, yeah, it would
right?
be more tricky, but yes, it would reveal some information. You're right.
Yeah. Okay. And so the question which I wanted to ask is about the timing attack that you mentioned. So since the apps are being executed remotely, so isn't the bandwidth from the timing channel really small? Because the attacker is always, we can't be sure whether it's the network delay or the execution time of the app that is actually being factored in.
So I'll get back to this, but this code, basically, what happens is that the code is executed in the cloud on some Node.js instance, basically. So when this piece of code is executed, you have access to this timing API, so this get time, right?
Yes.
So if you can measure the time here when the computation started and then when the computation finished, right? Then you can just do sort of compute the difference of the actual execution here. So it's not dependent on any network delays or anything like that.
Oh, I see. Okay, so you are assuming the attacker's code is also there on the same.
Because that's where it's ultimately executed.
Yeah. Okay.
But that's a good point.
Yeah. Thanks.
Thank you. Okay. But there is another question that you may be asking at this point, right? So so this is nice, but so you have to find a way to trick the user, right, to install this malicious app. So it happens quite often, but I think that's a reasonable sort of skepticism, right? And indeed, what we try to do later on is to understand a little bit the attack surface better here beyond, this URL attacks that I just showed you. So could it be possible that if we have a user, say myself as the attacker installing one of these apps, could it be possible to attack other apps from other users running in the same platform? Okay. So here is sort of just a picture of how this architecture looks like more closely. So for IF, Zapier, and Node-RED. So here we have 3 apps. So the first one is, so for any file you store to Dropbox, then it will send it to you via email. The second one is you have some surveillance camera saying that if motion is detected at home, then you notify the user by sending an SMS. So these are 2 apps of one user. And then maybe a third user is having this third app, I don't know, if it's 7 a.m. in the morning, then just send an email to, I don't know, the babysitter or something. Okay. So when we look closely at these platforms, then Zapier and Node-RED, so these are 2 other platforms I didn't mention, these are single tenant. So what does this mean? It means that when the app is executed, say in some cloud platform, then the apps of the same user are executed on the same Node.js instance in this case. While in the case of IF, this is multi-tenant, meaning that you could have apps from different users running on the same instance. And there are sort of economic incentives here when it comes to executing these apps in the cloud, because the more instance you use, the more you'll have to pay and so on. So the model I showed you so far is this malicious app maker, which would sort of execute an app, have the user install a malicious app, and then execute through these URL attacks. So let's just look a bit deeper how this works in the cloud. So basically what's happening here is that, the code of the app is being run inside these AWS Lambdas. So you have a Node.js instance running in Amazon's version of Linux here. And these Lambdas are sort of sandbox that process Lambda. So really what's happening here is that you have some run script code function that takes the code that you as a user or the attacker wrote, some configuration passing the parameters like the URL of the photo in this case, and then executing it. So logically, it's like doing a val on the script code using this configuration here. Okay. So now they've thought a bit about security. So they use TypeScript. So code is type, and they disallow obvious sort of APIs for exfiltrating information like eval, modules, sensitive APIs like set timeout and so on, and IO in general. Okay, so in the use case I showed you so far, and all these three platforms are susceptible to this, is that user installs the malicious app, and then basically the attacker will sort of compromise the trigger and the action of this app. Okay, so nothing new so far is what we've been discussing. Well, it turns out that for platforms like Zapier, so what happens here is that different apps from the same user are run on the same instance. So if you're able to break out of the same sandbox, and I'll show you that we can, well then, by having the user installing only one malicious app, you can compromise trigger and action data of all the other apps of the same user. Okay. When it comes to IFT, basically the platform you've been talking so far, their situation is a bit crazier, because now the user can install only benign apps. So, nothing has to do with attacker control code here, but basically the attacker is able, by installing himself a malicious app, to read data of other apps from other users. And the spoiler here is that because these apps are different apps from different users, are executed on the same instance of this Node.js, then if you manage to break out of the sandbox here, well, then you have access to all this data. I won't get too much into the details of how this is done, but the basic idea of the breakout here is based on this vulnerability of prototype poisoning or prototype pollution, basically. So in languages like JavaScript, where sort of inheritance is implemented through prototype chains, then if you manage to pollute the prototype with your values, then you can have security vulnerabilities like breaking out of the sandbox, basically. So what we do here is we do some JavaScript magic to sort of bypass the security checks that IFT has added, and then once we pollute this prototype, then we're able to read, all the triggers and action data that are executed within the same Node.js instance. Okay, so there are some details here. So this is really bad. We notified IFT about this. And then their response basically was to run the code within the sandbox. So VM2 is one of the known ones providing isolation. It has some drawbacks, but for their setting, I think it works pretty well. So this solution would sort of solve the problem of having apps reading data from different users and different apps. But yet, the attacks that I showed in the first part, that those are still possible. Okay. So unfortunately, all of these two platforms, they are closed source, so one cannot experiment much with them. But there exists one that is open source, and it's called Node-RED. So here the attacks are pretty simple and straightforward because the platform itself was not built with security in mind. So here you could have just one malicious app reading data from other apps and also from the platform itself. So you can make the platform crash and so on. Okay, so what do we do about this? Well, we played a bit with fine-grained sandboxing for JavaScript. So this is at the language level. And the basic idea here is, I'm sorry, you sort of trap all the interaction between the hosts. In this case, would be Node.js and the execution of this app. So sandtrap is sort of sandboxing mechanisms that we've developed, sort of building on this VM2 and closing off some of the vulnerabilities there. So this is really tricky in general. I mean, for people who have worked on sandboxing for JavaScript, it's almost a mission impossible. But for platforms like IFT, you know, there are some features there. So you have no modules in general, and you don't have APIs other than the ones sort of corresponding to these triggers and actions that I explained before. So in that setting, at least, it works pretty well. Okay, so just to wrap up this part conclude shortly. So all these platforms are vulnerable to attacks, basically through for different users, you know, across different apps. So in this sandtrap, we developed this flexible sandboxing mechanism based on some formal core. Expressing policies at different levels, so ranging from modules to different APIs and so on. So it's a proxy-based implementation in JavaScript for those of you who are familiar with the setting. And then what we do there is see how different platforms like IFT, Zapier, and Node-RED would benefit from some solution. From this solution. So for IFT, it works pretty well. For the others, there are some challenges in terms of what the effort that the developer has to put on, but that's what you have to pay for security. So if you're more interested into this topic, then there is a paper from Using Security last year to sort of take a look at. Okay, so just to conclude here, so final remark is, so we showed all these attacks, right? So the whole story here relies on trusting the cloud platform with user-sensitive data. So if you remember when I started, right, is that the user, by accepting to execute this app, give to the platform complete control over the Google Drive, you know, and the iOS photos and so on. So is that a good thing? And that's quite dangerous, right? And not only because you shouldn't trust the cloud platforms, but sort of, we've seen that these platforms get compromised, and sort of an attacker could maybe steal all these tokens and sort of do, perform a lot of malicious actions for millions of users in this case. So one interesting research question, which has been addressed by others in this case, is how do we limit the trust into the cloud platform? So if you're interested in this topic, there are these two papers. So the first one is just looking at secure multi-party computation, so how to use garbled circuits basically to do this computation over encrypted data. So maybe this sort of partially or adds to the question that was asked before. So what if the data is encrypted? Well, then you'll really have to find a way to perform computation over encrypted data because it's needed. Another interesting approach is to how to minimize the data that the platform has access to. So what happens in this case, and this is classical for usability, right? So if you want to give the platform access over, say, your Dropbox, then you have an API or you have a token that gets, read access, write access to everything basically on your Dropbox, right? So yes, and this sort of makes sense for usability reasons, but when it comes to security, then once the attacker gets hold of the token, right, then they can do pretty much everything. So what the second paper studies here is how can we minimize the data that is being sent to the platform. So this study is sort of language-based minimization, meaning that if you know the specific triggers and actions, right, that are being executed, well, maybe on the client side, you can already send the necessary data, say the link to the photo, but then when it comes to other other parameters or features of your Dropbox, then you provide fake data, for instance. Okay, so, which shouldn't affect the functionality of executing this app. And then sort of a third line of work, which we are studying here at KTH, is more related to the first one, is how can one rely on this trusted execution environment? So these are sort of hardware support that allows you to execute, say, code securely over an untrusted cloud, for instance. So we're looking into ways how one could get the same guarantees as secure multi-party computation, but maybe with lower performance cost. Okay, so that's all I had to tell for today. So thanks very much, and yeah, I'll be happy to get some questions.
Thank you very much, Musard. So any more questions? As usual, you can just unmute yourself and ask the question.
Hi, I'm one of the professor. My name is Victor. I just have a question regarding to the work you've done. I wonder, have you done a thorough test or maybe ethical hacking? Because what you've done is that you define from the architecture, from the coding side, but then what is lacking is just a lot of comprehensive tests, including ethical hacking. So I wonder, are you doing the kind of test?
Yeah. So of course, this is done in an ethical manner. So for some of the attacks, we collaborate with the owners of these platforms. But also the attack I showed you before, right? So maybe I should have explained this before. So what's happening there is that I am installing the app myself, and it's executing it on my own sort of Dropbox and photos in a sense. So yeah, absolutely. We have,
okay, it would be good to see, because the issue with IoT is that it opens up a lot of possibilities. So it means that there are more combination, and quite often hackers they do a couple of hacking techniques altogether, so that you have to have more defense and maybe more tests. Yeah,
okay. Absolutely. But it's we have to do it ethically, of course.
Okay, thank you so much. Thanks.
You're welcome.
So Musard, oh yeah, Omar, please go ahead.
No, please go ahead, Vineet. Go ahead.
Okay, thanks. So Musard, like you mentioned, there is plenty of work already in the space of JavaScript, for information flow control and so on. So I was wondering, were there any new insights to be learned when it comes to IFTTT or such platforms, as far as information flow is concerned, in terms of maybe some ways of enforcing it in a more efficient manner or something like that?
Yeah. So I guess the advantage you get here is that if the code is not malicious in a sense, right, then the structure is pretty regular and the code is not super big. So there are clear advantages there. But other than that, and I'm talking about if now, when it's sort of pure TypeScript code, so there are sort of some of the challenges. I mean, you could have all the challenges we know about when it comes to information flow for JavaScript, but for regular code that we found there, I think that doesn't occur much. So it's more the size when it comes to it. When it comes to other platforms, well, it gets really tricky, and I'm not even sure information flow is going to fly here, because if we think of Node-RED, so this is a bunch of NPM packages basically put together that are integrated, in an application. And there you need methods to significantly, extend your information flow control to handle that domain.
Right.
That's why
Thank
we're
you.
going for sandboxing here, basically.
Yeah. Sure. Yeah. Thank you.
Yeah, thanks. Good to see you, Vinet, by the way.
Yeah. Good to. Maybe we'll have a chat offline. Yeah.
Yeah, I just wanted to follow up on Vinny. It's a great talk. So whenever we've used if this and that, one of the challenges we often have is the timing delay. So for example, when we invoke, for example, one application from another, often the time processing that is required for, say, using Gmail or using Twitter feeds and so on is very unpredictable. Sometimes it even happens that, we send a trigger event today and we hear tomorrow, so the question is, right, that really the JavaScript part that you suggest, is not just applicable to, of course, if this and that or node, right? It could be applied to any environment, that supports JavaScript processing. But I was just wondering, how reliable do you think if this and that is, and especially in the context of the timing issues that you mentioned?
So in our research, actually, those sort of long time delays are an advantage to justify it, because of course, when you implement a runtime monitor, then it adds some overhead, right? And at least officially, what IFTTT say is that they guarantee that the applets are executed within 20 minutes, but most of the time it's a matter of seconds, right? As you saw in my in the example I showed you before. So that's very much a black box. Yeah, I cannot comment much about that. It's strange to hear that you have had problems sort of taking days to execute an applet.
Well, yes, absolutely. Okay. So when we sometimes trigger events with Google, so we triggered on keywords in Twitter. So we sent a Twitter message, we searched on keywords to trigger off another application, but sometimes it can take, very long and unpredictable periods. So I was wondering whether, you wonder whether this is due to some interception of the message, or whether it's just because of the delay in processing by the applets themselves. So yeah.
Yeah, it's hard to tell, right? So when it comes to the cloud platform, of course, what's going to happen is that they will be assigned to some Node.js instance if it's available and so on. So there could be some delays there, but network delays could play a role too. I'm not sure I'm giving an answer that makes you happy, but what I can say is I can give you a pointer basically. So. There are people at Purdue University that are looking into this kind of issues. So Berkay Çelik is one of the researchers looking into this. So maybe some of his research could apply here.
Thank you very much.
Okay.